Okay, so now there is a couple more theorems here, and this part is called the limits of. It's called the limits of trigonometric functions. Of trigonometric functions. Now the following facts, as stated as theorems about functions in general, come in handy calculating limits of some trigonometric functions. So these seems to be some facts that will be stated as theorems, and these are about functions in general. So these are about functions in general. So these are, you could say, some theorems about functions in general. About functions in general, and these will come in handy for calculating limits of some trigonometric functions. Will be used in calculating the limits of some trigonometric functions. Trigonometric functions. So, theorem number 3 is let f and g be two real valued functions. Let f and g be two real valued functions. Real valued functions. So a real valued function, so we have basically two types of functions, as you know, when it comes to basically having this sort of designation. We have something called a real function, and we have something called a real valued function. So a real function is basically the kind of function where basically the range of the function, and let me take a look at this. Actually, I'm not really sure about this. So we had basically one definition before in class 11 chapter 2. In class 11 chapter 2, which is about relations and functions, we had a definition number 6. We had the definition number 6, which says that a function which has either R or one of its subsets as its range is called a real valued function. So a function which has R or one of its subsets as its range is called a real valued function. It's called a real valued function. So, and further, if its domain is also either R or a subset of R, further, if its domain is also R or a subset of R, it is called a real function. is called a real function. So what that means is that, so basically a function which has R or one of its subsets as its range, basically which has R or one of its subsets as its range, is called a real valued function. Now this real valued function, if the domain of this real valued function is also R or one of the basically subsets of R, then it's called a real function. So that means that here when we say that let f and g be two real valued functions, that means that the range of this function is R, or basically a subset of the set of real numbers, right? Now what we have over here, the definition that we were talking about, is that, so we said that let f and g be two real valued functions with the same domain, and such that f of x is less than or equal to g of x for all x in the domain of definition. For all x in the domain of definition. For some a, so basically f and g are two real valued functions, meaning that the range of these two functions is the set of real numbers, or a subset of the set of real numbers, and now basically, and they have the same domains. F and g basically have the same domains, in such a way that f of x is less than or equal to g of x, meaning that the value of f of x at all points across the domain of the two functions, and of course they have the same domains, value of f of x cannot at any point cannot exceed the values of g of x. F of x is always below g of x, or at most equal to g of x. So, and that is for all x in the domain of definition. Now, then you can say that for some a, if both basically limit of f of x as x tends to a, and the limit of g of x as x tends to a exists, then the limit of f of x, as x tends to a is less than or equal to the limit of g of x as x tends to a. And well, if you want to see an illustration of this, you can consider this illustration, meaning that, for example, let's say that this is x, o, and y, and let's say that this function over here is, for example, this function over here is y is equal to g of x, is y is equal to g of x, and we have another function here that is, for example, which is y is equal to f of x, and at this point, for example, at this point a, let's say that this point is a, and let's say that, and if you take a look at the definition or the theorem, so f and g are real valued functions. Their range is the set of real numbers or some subset of that, and they have the same domain. Their domain is the same. Their domains are the same, in such a way that f of x is less than or equal to g of x. As you can see that f of x at all points, this function, these two graphs show that, or actually are supposed to show that f of x is less than or equal to g of x for all x in the domain of definition. Now for some a, for example, if both the limit of f of x as x tends to a and the limit of g of x as x tends to a exist, then the limit of f of x as x tends to a is less than or equal to limit of g of x as x tends to a, and that is basically theorem number 3. And of course we will actually use this theorem in finding some basically limits of trigonometric functions. Now, the next theorem that we have is theorem number 4. Which is theorem number 4, which is called the Sandwich Theorem. The Sandwich Theorem. Now, what this theorem says is that let f, g, and h be real functions. Let f, g, and h be real functions. Real functions means that the range of the three functions are basically is the set of real numbers or some subset of the set of real numbers, and further also the domain of the three functions is the set of real numbers, and or basically some subset of the set of real numbers. So if f, g, and h are real functions such that basically f of x is less than or equal to g of x is less than or equal to h of x for all x in the common domain of definition, for all x in the common domain of definition, for some real number a, of course this is the sentence is not, this is over. So let f, g, and h be real functions such that f of x is less than or equal to g of x less than or equal to h of x for all x in the common domain of definition. Now for some real number a, if the limit of, for some real number a, if the limit of f of x as x tends to a is equal to the limit of h of x as x tends to a, then, so the limit of f and h are the same, then basically you can say that then the limit of g of x as x tends to a is equal to L. And these are by the way equal to L. So So if the limit of f of x as x tends to a is equal to L is equal to the limit of h of x as x tends to a, then the limit of g of x, which is basically sandwiched between the two functions, is also equal to a, which is basically as of course as x tends to a. And an illustration of this would be as follows. So for example, you have the y-axis here, you have O and x here, and suppose that you have basically some function over here, and let's call this, for example, y is equal to h of x, and then you have another function which is basically f of x, for example, something like this, some function like this, for example. This is y is equal to f of x, and we said that basically f of x is less than g of x less than h of x, meaning that f is below these two functions, or at least less than or equal to these two functions, and g and h are basically there as well. So there you will get basically, there you will get g is right between the two functions. So this would be y is equal to g of x, right? And of course, maybe my illustration is not perfect, but you can see over here, and hopefully you understand what this means, is that f is less than or equal to g of x is less than or equal to h of x, okay? So if that is the case for all x in the common domain of definition, now if you have some real number a, for example, let's call this a, and basically if the limit of f of x is equal to the limit of h of x, and you know that basically g is sandwiched between the two, and the limit of f of x is equal to L as x tends to a, the limit of h of x as x tends to a is equal to L, then the limit of g of x as x tends to a is also equal to L. So that is basically this theorem here. And given below is a beautiful geometric proof of the following important inequality relating trigonometric functions. So now this trigonometric function, of course, it has nothing to do with this theorem whatsoever. This theorem is over. This is a little bit misleading, but there is this inequality that contains all of these trigonometric functions that comes in handy sometimes, and that is basically you have cos of x is less than sine x by x is less than 1 for 0 less than the absolute value of x less than pi by 2. Okay, so this is the inequality, and the proof for that is as follows. So you have a circle here. You have a circle here, and let me draw the circle this way. You have a circle here, and hopefully we can order 1, and then I think, okay, so we have a circle here, and then the radius of the circle is basically, this is the radius of this circle. And there is a point on the circumference of this circle. Let's call it, for example, point C. You can call it point C here. And you could construct a triangle over here. And if I draw a perpendicular to this line and connect these points together in such a way that this line goes through the point here, I will have this triangle here. I will have this triangle here. Now, basically we can give these some names. For example, we can call this angle X, this point O, this point, for example, and you can drop a perpendicular to this from here and call this point D, for example, this point A, this point you can call C, and this point you can call B. And basically, that's basically what you have here. Okay, so we want to basically prove cos x is less than, basically sin x by x is less than 1, and we want to prove that for this interval, or this interval of 0 less than or equal to 0 less than basically the absolute value of x and less than pi by 2. Now, since this interval is saying that basically the absolute value of x, then naturally, of course, you will have two cases here, meaning that either x is negative, meaning that if x is less than 0, then of course you know that the absolute value of function, the absolute value of x is equal to basically x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. That means that if x is less than 0, then the absolute value of x would be negative x, which means that for x less than 0, the interval becomes 0 less than negative x less than pi by 2, and so what that means is that then multiply by negative 1, you will get 0 is greater than x greater than negative pi by 2. And write this the other way around, you will get negative pi by 2 is less than x less than 0. That means that if x is equal to 0, then negative pi by 2, the interval becomes negative pi by 2, less than x less than 0. And now, since x is negative, we have, instead of x, if I write negative x, then over here I have cos of negative x is less than the cos of negative x is less than sine of negative x is less than sine of negative x over negative x less than 1, and you know that cos of negative x is equal to cos x, and sine of negative x is negative sine x, and over negative x is less than 1. These two you'll cancel out, so you have cos x is less than sine x by x is less than 1. Now, if x is greater than 0, then you have basically 0 is less than x less than pi by 2. 0 is less than x less than pi by 2, and And so then you have basically simply cos of x is less than, you have cos of x is less than sine x by x is less than 1. So ultimately, whether x is positive or negative, then you will have to, then basically you will come across the same relationship between cos x, sine x by x, and 1. And therefore it's not necessary to prove this for negative x's and positive x's. Just for one of them would be enough. So we will prove this. We will prove the inequality. So we will prove the inequality. For basically for 0 less than x less than pi by 2. Now let me erase all of this, because if basically proving the inequality for 0 less than x less than pi by 2, we have, so this is basically the construction that we have. And in this figure, O is basically the center of a unit circle. O is the center of a unit circle such that the angle AOC, this angle here, is x radians. And x is greater than 0 and less than pi by 2, basically radians. So you can say that 0 is less than x less than pi by 2 by construction. Now line segments BA and CD are perpendiculars to OA, and further we join AC. So AC is also joined, this line segment. And so we can say that the area of triangle OAC, which is basically OAC, this triangle over here, the area of triangle OAC, the area of the triangle OAC is less than the area of the sector OAC, is less than the area of sector OAC. Sector OAC would be basically this sector over here, and of course the area of the sector is greater than the area of the triangle, because because the triangle is actually a part of the sector, right? And then you can say that all of these are less than the area of the triangle OAB. Triangle OAB would be this large triangle over here. The area of triangle OAB. Now the area of triangle OAC, which is this little triangle here, it's equal to 1/2 of the base times the height. So the height is CD and the base is OA. So that is 1/2 of OA times OA times CD. 1/2 of OA times CD. And the area of this sector here, the area of this sector OAC, is basically x divided by 2 pi radians times the whole area of the circle. You see, the whole area of the circle is pi r squared, is basically pi r squared square units, right? So the area of the whole circle, the area of the whole circle is equal to pi r squared units. Now, if the area of the whole circle is pi r squared units, then the sector is basically a ratio of the whole of the circle, and the ratio would be x to the whole circle would be one complete revolution would be 2 pi, and so the sector becomes x divided by 2 pi. So then that means that, for example, if you had a circle over here, and this is the center, and this is the radius, then 1/4 of the circle, which is a 90-degree angle, that would be basically the whole area of the circle would be pi r squared. Now 1/4 of the circle would be basically this angle is pi by 2, and the whole angle, the whole revolution would be 2 pi. So pi by 2 divided by 2 pi is pi by 2 times 1 by 2 pi. Pi and pi cancels out, that's 1/4. So you can see that a 90-degree angle is 1/4 of the circle. On the other hand, for example, if you were calculating the area of this sector of the circle, then this angle would be basically pi radians. The whole revolution would be 2 pi radians, and so 2 pi and pi would cancel out, and you would be left with 1/2 of the circle. And of course, you can then, since you know that this is 1/2, you can multiply it by pi r squared, and then that gives you the area of the half of the circle. Otherwise, this is just a ratio. So with that in mind, what we can say is that basically the area of this sector OAC is x by 2 pi times pi r squared and of course r squared would be OA, so I can write this whole thing as pi, and pi I can cancel out. Instead of r squared, I can write OA squared, and therefore this becomes x divided by 2, for example, times or let me actually write it the way that they have written it, because they might actually have used it in a specific way. So you can write x divided by 2 pi, which is the ratio, and then pi r squared. R squared would be OA squared, right? And the area of the triangle OAB is basically this big triangle over here, is 1/2 of the base, which is OA, times the height, which is AB, right? Now, that means that basically dividing through by OA, by OA, we have we have basically 1/2 of CD is less than basically, so OA, one of these OA's cancels out, pi and pi cancels out, so you have 1/2 of, and then also multiplying by 2 and multiplying through by 2. So let's do that part first, and then we will multiply. We will do this part next. Okay. So then you have 1/2 times x times OA, and then divide by OA. You have 1/2 of basically AB. And now if you're multiplying through, multiplying through by 2, we have, so you would get CD is less than x times OA is less than AB. CD is less than x times OA is less than AB. Okay, so that is one thing. Now from triangle OCD is basically this triangle over here. So you can say that from triangle OCD we have basically sine x. Sine x would be basically CD by OC, or by OC, and OC is the same thing as OA, because both of these are basically the radii of the circle. So you can say CD by OA. So sine x is equal to CD by OA, and hence you can say that CD is equal to OA times sine x. Also tan of basically x, tan of x is equal to, so tan of x is equal to the amount of the tan of this angle in this triangle OCD would be the amount of rise divided by the amount of run. So the amount of rise is CD, the amount of run is OD. Or basically CD, you can write it as now they have taken this in the larger triangle, meaning that AB by OA, and so in triangle OAOB, so from triangle AOB, basically tan of x is equal to the amount of rise by the amount of run. OAB, this big triangle here, the tan of x is the amount of rise is AB, the amount of run is OA, so AB by OA, and hence basically AB is equal to OA times tan x. So this is CD, and this is AB, and this is CD, and this is AB. And so we can rewrite this, for example 1 as as CD is equal to OA times sine X less than X times OA less than AB is basically OA times tan X. And now we can divide, I suppose, by OA. Since OA is and you need to pay attention to the fact that OA is positive because it is a length. Since it is a length, of course it is positive. And dividing by OA, we have, so if OA was negative, then of course, for example, if you say that 1 is less than 2, less than 3, if you divide by 3, for example, divide, basically dividing through by 3, which is of course a positive number, we have 1/3 is less than 2/3 is less than 3/3. 3/3 is equal to 1. 2/3 is less than 1, and 1/3 is of course less than 1. So this is true. Now the same inequality, 1 is less than 2 is less than 3, if I divide by negative 3, dividing through by negative 3, which is less than 0, we have negative 1/3 less than negative 2/3 less than negative 3/3. Now this is equal to negative 1, and here we are saying that negative 1/3 is less than negative 1, which is not true, and negative 2/3 less than 1, less than negative 1, not true, because negative 1/3 is actually greater than negative 1, negative 2/3 is actually greater than negative 1. So that means that in inequalities, whenever you divide or multiply by a negative number, you have to basically change the direction of the inequality sign, meaning that dividing by negative 3, you would have negative 1/3 is greater than negative 2/3 is greater than negative 3/3. And now this is negative 1, and of course negative 1/3 is greater than negative 1, negative 2/3 is also greater than negative 1, and this is true. So now, basically having that in mind, since we know that OA is basically positive, and we want to divide by OA, so then the direction of the inequalities do not change, because it's a positive amount, a positive quantity basically. So you have sine X is less than X is less than tan X. Now if I divide by sine X, I suppose, now you can of course argue that, so this I call 2, for example, you can argue that since 0 is less than X less than pi by 2, sine X is positive. Since 0 is less than X less than pi by 2, then sine X is positive, because you are in the first quadrant. And thus by dividing through by sine X, and thus by dividing through by by sine x, we have, now these are the kinds of mistake that most probably, for example, Einstein made. And the first time that he published the special theory of relativity, the theory was actually wrong because his mathematics was wrong. There was some mistakes in his mathematics. And they didn't get to test it anyway. But even if they had tested it, he would have been proved wrong. And the only reason was that basically his mathematics was basically wrong, and then somebody else found the mistake for him. I think his wife or somebody else, they found the mistake for him. And there is one thing, basically, there is logical errors that you can make in mathematics. There is also these kinds of mistakes. For example, right now, I wanted to divide by sine x, but I forgot to check whether sine x is a positive value or a negative value based on the angle that I had. So you have to be careful, of course, because mathematics, actually, if it's wrong, it just simply doesn't work, and then you don't know what's going on in your work. So basically, if you divide by sine x, we have, so dividing 2 by sine x, we have 2 becomes, so sine x by sine x becomes 1, less than x divided by sine x, less than tan x divided by sine x is basically tan x divided by sine x is tan x times 1 by sine x, which is equal to sine x by cos x times 1 divided by sine x, and that is 1 divided by cos x. 1 divided by cos x. So, now the next step would be if you take the reciprocal of these, you would have, taking the reciprocal again does change the direction of the sign, meaning that you would get, taking the reciprocal of 1 is 1, and then you would get greater than, the reciprocal of x by sine x is of course sine x by x, and again greater than cos x, right? And now I can rewrite this the other way around without changing anything, just put cos x over here, less than sine x by x is less than 1. So that is basically what we wanted to prove, and which completes the proof. Okay, so that was theorem number 4. That was theorem number 4. And we have there are 2 more theorems here, and I think we will prove them as well. So theorem number 5. And we have basically the following are 2 important limits. So number 1, we have the limit of sine x by x as x tends to 0. This is important. A lot of applications. The limit of sine x by x as x tends to 0 is equal to 1. and also the limit of basically 1 minus cos x over x as x tends to 0, that is equal to 0. These two are absolutely important. You need to remember them. Okay, so now to prove number 1. To prove number 1, we have basically the Sandwich Theorem. The Sandwich Theorem, we said that basically the f, g, and h were real functions, and basically we said that f of x was less than or equal to g of x, less than or equal to h of x. Then we said that if the limit of f of x when x tends to a is equal to L is equal to the limit of h of x as x tends to a, if that is the case, then you can say that the limit of g of x as x tends to a is equal to L. That was the Sandwich Theorem. And you need to excuse my pen. It's not writing very properly. I need to restart my computer probably after this recording. So this is the Sandwich Theorem. Now, using this, we can say that and also we know that the sine there was some other basically theorem that we had, and that was about sine x by the one that we just proved, which is basically we said that cos x is less than sine x by x is less than 1. So these are basically 3 functions. So now if using the Sandwich Theorem, you can see that we said that if basically the limit of this function is equal to the limit of this function, and this function is between the two, then the limit of the function which is between the two is equal to the limit of the other 2 functions. Now you know that the limit of 1 as x tends to 0 is equal to 1 because it's a constant function, and the limit of cos x as x tends to 0 is actually equal to 1 because even the value of the function cos x at 0 is actually equal to 1, and at 0 the cos function is actually some function like this that reaches basically that approaches the value 1 here. Then this is 0 and this is 1, right? So the limit of cos x as x tends to 0 is also equal to 1, which means to say that basically the limit of 1 as x tends to 0 is equal to the limit of cos x as x tends to 0. So now, since this function is between the two functions, then you can say that the limit of, based on the Sandwich Theorem, you can say that the limit of sine x by x as x tends to 0 is actually equal to 1. And that way you can prove this theorem. It's pretty simple, although I followed the way that they have put everything together, but well, pretty simple. Now to prove number 2, which is so far we have proved that the limit of sine x by x, we have proved that the limit of sine x by x as x tends to 0 is equal to 1. That is one thing that we can use in many different types of situations. Now the second thing that we want to prove is the limit of 1 minus cos x over cos x as x tends to 0 is equal to 0. So we want to prove that number 2, to prove that the limit of 1 minus cos x over cos x as x tends to 0 is equal to 0. So we need to do a little bit of trigonometry here. Okay, so now in order to prove this, so you hopefully remember that we had a couple of basically trigonometric ratios and identities, and that was class 12 chapter, I think. I don't know which one that was. Trigonometric functions, inverse trigonometric functions. Okay, I think this one. So you know that basically cos of 2x is equal to 1 minus 2 times sine squared x. You know that basically cos of 2x cos of 2x is equal to 1 minus 2 times sine squared x, which means that cos of x is going to be half of this angle, would be 1 minus 2 times sine squared x divided by 2. And then basically taking basically cos x to this side and negative 2 sine squared x by 2 to the other side, you get 2 times sine squared x divided by 2 is equal to 1 minus cos x. So that is basically, or you can write 1 minus cos x is equal to 2 times sine squared x divided by 2. So that identity we can use here. So basically now we wanted to show that, to prove this identity here. So I can write basically the limit of 1 minus cos x over cos x as x tends to 0 is equal to the limit of 1 minus cos x. I write it as 2 times sine squared x divided by 2 times divided by cos x. Actually this is supposed to be x, I suppose. I think I made a mistake here. This is actually supposed to be x. Let me see if the This is actually supposed to be x, right? I apologize for this. So the limit of 2 times sine squared x divided by 2 by x as x tends to 0, and so if you bring this 2 to the denominator, it becomes basically this becomes the limit of basically sine squared x divided by 2 by x divided by 2 as x tends to 0, and then you can write this as the limit of, so this is sine squared x divided by 2 by x divided by 2, which is basically the same thing as the limit of sine of x divided by 2 by x divided by 2 times the sine of x divided by 2. So that would be this limit as x tends to 0. And then and then I can write this as the limit of sine x divided by 2 by x divided by 2 as x tends to 0 times the limit of the sine x divided by 2 as x tends to 0. So we said that basically the limit of sine x by x as x tends to 0 is equal to 1. We already showed this, which means that you can say that then the limit of, instead of x, you can of course say x divided by 2, x divided by anything. The angle, it's just important that the angles are the same basically. So which means that basically this becomes 1, and the limit of sine of x divided by 2 as x tends to 0 is the same thing as the limit of sine x as x tends to 0, of course, and then sine 0 is equal to 0, so this becomes 0. So then you have 1 times 0, which is equal to 0, and therefore you can say that the limit of 1 minus cos x over x as x tends to 0 is actually equal to 0. That is what we wanted to prove. Now this step over here that I used, you can use if you don't feel comfortable using the logic that I use. Of course, I didn't explain my logic to you, but in order to get the limit of this function, the limit of basically sine x divided by 2 as x tends to 0, you can put, basically you can here put x divided by 2 as y. Now as x tends to 0, then of course y tends to 0, right? As x tends to 0, y tends to 0. Because as x tends to 0, this becomes 0, and then this is equal to that. So then you can write this as the limit of sine y as y tends to 0, then this becomes 0, right? Because at 0, basically, the sine function approaches 0. So then that becomes 0, and therefore this is equal to 0. And so that was basically all the theorems that we had here. Now we have a couple of questions here. We will do them in the next video, and then we have a couple of exercises. So I'll see you in the next video, and thank you.